Wonderful. Thanks, Jenny. Thank you so much in the central region. Many of your offices, I know you're very busy today, including near and close to home and campus here, being under not only a conditional tornado threat, but winter weather across many offices in the Central Plains. I really appreciate it. I want to talk today a little bit about hail, specifically a campaign that we proposed to the National Science Foundation back in 2018 and finally got across the finish line in terms of funding. Called ICECHIP, the In-situ Collaborative Experiment for the Collection of Hail in the Plains. I'm one of the science PIs leading this effort along with about a dozen other institutions and even collaborators from the Weather Service. So I hope today to just really give you kind of an overview of what we're expecting to do in terms of science and potentially offer some ways that your local WFOs can collaborate with us. We will be out in the field basically chasing hail from May 15th to June 28th, so a rather long field campaign. And it's very likely that at some point during that process we'll be somewhere, many of you WFOs in the central and even southern region. Some of the science PIs are listed at the top. These are individuals that have contributed significantly to the proposal and the science objectives that I'm going to walk through here in just a second. We also have a lot of collaborators that are sort of external to these science steering committee projects, but also will play a significant role in the observational component of being in the field and capturing specific needed observations associated with our science themes. So thank you to all of them. I know many of you, even on this list that I see here through the chat or participants, are actually even involved in writing letters of support. I've reached out to many of you, and many of you have actually provided letters of support for this campaign when we were trying to get it off the ground with the Weather Service or with the National Science Foundation. It has been, I think, the last 6 months of my life, if not a year, have been really herding cats. It's getting a lot of moving parts, getting ready for people ready to get out into the field and take observations. So let's jump in. Some of the goals, I think science goals that we really have for ICECHIP really relate around the fact that we just don't have a lot of significant coordinated hail field observations. You really have to go back to the Hailstone project that Jenny was involved in, SHAVE, which was an effort in the mid-2000s at NSSL to really get high density hail observations. Prior to that, you really have to go to like the North American Hail Research Experiment, or CCOPE, in the 70s and 80s in Montana and Colorado. And of course, not only has Doppler radar technology significantly increased since then, but we also have different observing platforms like hail impact astrometers and drones that we really are excited to deploy to try to capture some of these missing observations. So I think, one overarching goal that has a direct implication for warning practices is or even assessment of, a historical convective day, is to try to improve mesh. Mesh is an interesting product that a lot of people put a lot of weight in, but doesn't have a significant long history of being calibrated, especially across multiple geographies. So we hope to really improve mesh, the mesh algorithms that are used in day-to-day operations. In addition to that, this is not just a radar thing. We also hope to improve remote sensing detection of hail swaths from satellite. That will mostly be from commercial low Earth orbiting satellite or even geostationary if the swath is large enough and the vegetation cooperates. I'm particularly interested, and this came out of a users committee meeting that some of you were a part of, this idea of first warning trigger. So if you're at the warning desk and you're watching satellite, and you're watching glaciation perhaps in satellite products, and you're watching radar, at what point do we, at what point in the updraft phase do we actually trigger first warning for severe hail? So I think that will have a direct impact on hopefully the science that comes out of ICECHIP will help inform that first warning trigger that many operational meteorologists rely on. From a science and modeling perspective, constraining our microphysics schemes, so some of these double moment microphysics schemes that are making their way into various ensemble members of CAMs and are really poorly constrained because we don't have the observations necessary. This could be from a stochastic sense in our numerical weather predictions physics schemes, or just better understanding hailfall distribution and size. And that's really because we don't have a great understanding of a specific distribution of swath associated with a particular convective storm. This goes back to Stan Shagnon's work in the 60s and 70s of trying to characterize hailfall using hail paths. And while there have been efforts like IBHS to characterize these and SHAVE and other projects, we hope to really have a multifaceted, multi-observational component to this. So in addition to hail pads, impact astrometers, what was the radar showing at this time of hailfall? I'll talk a little bit more about those observations in just a second. Isotopic analysis, this is really the idea of thin sectioning with hot wire hailstones and then melting them down to try to better understand water vapor isotope and oxygen isotope analysis to better correlate where that particular growth ring occurred at what temperature, and then we can kind of back out some hailstone trajectory analysis with that isotopic. That'll be stuff that's done after the field campaign, after these hailstones are collected in the field. I've already talked about the hail size forecast, but in general, we really would like to sample lots of different convective modes and different environments. So environments that have very high boundary layer mixing ratio versus your drier, steeper lapse rates, perhaps that you'd find on the high plains, and different convective modes. So we'd love to deploy on left-moving supercells, right-moving supercells, upscale growth, isolated mergers, all these types of different things. There's just in a perfect world, we'd have all these different IOPs that sample these different convective modes and environments. Let me talk a little bit about the observations that we hope to gather in ICECHIP. So one of the things that we'll need to do, especially from a modeling perspective, is just better understand the pre-convective and evolution of the convective environment. This will be primarily done with mobile sounding systems, so wind sounds and full tropospheric depth radiosonde observations that we will have in the field. So deploying these 1 to 2 hours prior to CI and then launching every single hour in the uncontaminated inflow environment would be the goal for these large scale full tropospheric depth soundings. And then near storm, we hope to launch several wind sonde observations that can get close to and perhaps in the thunderstorm updrafts that can help us constrain our vertical velocity measurements that we're seeing from some of the Doppler radar measurements. So this is kind of standard of all field campaigns, right? You really want to understand what the convective environment's doing so that you can initialize models and do data denial experiments to better understand if you did have these observations available to you, do they improve the forecast? Do they reduce the uncertainty? And all these different kinds of questions. And of course, as many of you know, the near storm convective environment can be very heterogeneous in terms of quality and difference of things as simple as boundary layer moisture. I would say the most important aspect of the project will be gathering very near storm remote sensing observations using the University of Alabama Huntsville Doppler radar fleet. This will be the first time that the CAL radar, which is shown here in the bottom left, will be deployed for a convective field campaign. The CAL is important because it's a mobile C-band radar. It takes about 2.5 hours to set up. There's actually a little crane that has to lift various aspects of the dish and build this. So it's pseudo-mobile. We can't pick up and move it, but we can deploy it the morning of in an area where we think we're going to be operating in perhaps the mid to late afternoon. And that C-band is important because we'll obviously have much less attenuation than we will from the mobile X-band fleet, which will be DAOs 6, 7, and 8, which have been primarily deployed in experiments like Vortex 2 and Perils and other field campaigns to study tornadoes. The X-band obviously has a pretty significant issue with attenuation, but that's where we hope to augment the wind fields. So doing things like dual Doppler analysis and even triple Doppler analysis to augment what we're getting, hopefully, with the CAL. So morning forecast will be very important to try to place the CAL in a favorable area that we would be operating in later on in the day. But these radar observations will obviously help us better understand what's happening in the hail growth regions and help us better understand the microphysics of these convective storms as we sample them. As we capture the hailstones at the ground, one of the planned measurement opportunities is to do isotopic analysis. So take these back to the NCAR cold lab, thin section them, capture the water vapor and oxygen isotopes in each of these growth layers, wet growth, dry growth, or in some cases, all wet growth or dry growth, and then bring that back to our trajectory models to help us better understand at what point did this hail growth layer, so to speak, form in the storm. That really is going to help us better understand what are the different pathways to get large hail. Is it very stochastic, or is there a pathway in a left-moving supercell that very much differs from a right-moving supercell, or how do different convective modes or mergers play a role in the trajectory that a hailstone takes through the growth region, and what are the rates of accretion or freezing that we tend to see in some of these different trajectory pathways. So this will be one of the larger, I think, coordinated efforts to try to get large and significant and gargantuan hail back to the lab to be able to do that type of analysis. To collect those hailstones, we have a couple of what are called super sites. We'll have about 4 of these super sites from the Northern Hail Project and Julian Brimlow up in Canada. He's bringing these down for ICECHIP, but the idea here is they're kind of like a mobile mesonet with a hail pad and a GoPro mounted on them. And as hailstones fall, they come into basically this funnel baffle type system that separates the rain and allows the hail to fall into a freezer. And as long as we can get to that freezer relatively quickly, we can get these hailstones on dry ice and get them back to the NCAR cold lab for thin sectioning. But these would be hopefully deployed, in like a cross-sectional sense across a road, so that we could sample different areas of the hail swath and capture these hailstones basically and get them on into a cooler as fast as possible. There will be a lot more hailstone collection, but these will be kind of the more sophisticated scientific instruments that will be capturing those hailstones. The Near Storm Hailson project is out of the Bureau of Meteorology in Australia. These are basically small little wind sondes that will be neutrally buoyant when launched into the updraft, and will serve as essentially a pseudo hailstone in terms of understanding trajectory. So we hope to really constrain and measure updraft vertical velocity and trajectory, as each of these hailsons will have GPS sensors in them and allow us to basically track the pathway through which these hailstones take in various convective modes. So this will be the first really full-scale attempt to use these hailsons in the field to better understand these different trajectories associated with convective modes. And of course, then we can relate that back to the radar data, the environmental wind profile data, and kind of create this beautiful 4-dimensional picture of what's happening in the near storm environment and in the updraft. After the hail falls, assuming that we can get there quickly and there's not a significant amount of melting, but with SIG hail, or even giant hail, this is usually not that big of a problem. As long as the precipitation shield is a very sharp cutoff, we can get drones up into the air. We will have 2 basic type of drones. One will be kind of your simple, DJI Mavic 2 that will be flying at low altitude. The other longer flying unmanned aerial systems will be provided by CU Boulder. This is called the Raven fleet. These Ravens fly at about 80 meters AGL and have 4 to 5K cameras on them pointing down, and we can get precision measuring, calibrated measuring from these low altitude, long flying drones to be able to characterize the cross-sectional hail swath. So the goal would really be to make several passes over the top of the hail swaths to measure hailstone size and distribution using drones in a very fast order that humans driving along the cross section would take much more time. So these pictures will hopefully be invaluable to us to characterize what the hail swath looks like, and then of course we can time it up with the Doppler radar data to get a better picture of what that hailstone footprint looks like compared to what the radar was showing at various altitudes at that time of fall. The other types of measurements that we really hope to get are really hail swath ground measurements and in situ. So this is essentially mobile pods that we will drop along the path, including hail pads every 100 meters. mobile impact astrometers. I believe we have 14 or 15 of those that I'll show you in just a second, to better calibrate what type of kinetic energy and impact potential energy we have when these hailstones impact the surface, and then characterizing that over the entire swath. So the idea would be to not just get the largest hailstones, but to understand the impact kinetic energy of even small hail at the edges of the hail swath. So there will be a lot of in situ planned measurements that are really going to be provided by instrumentation from UAH and also IBHS. Once we get those measurements, I think in terms of selling this for broader impacts, obviously from the Weather Service perspective, better, remote sensing is a huge deal when you're talking about things like mesh or improving CAM microphysics for hail prediction. But really, at the end of the day, bringing back those in situ measurements to the lab and understanding their impact on materials science. So IBHS will be doing a significant amount of laboratory testing during and after the experiment with these real hailstones that we collect to understand shingle impact and potential ideas for shingle mitigation and different classes of shingles based on real observed hailstones. So that was a pretty significant component to the post kind of field activities with the observations that we hope to acquire from ICECHIP. And I will move into some basic, textbook schematics of what we hope to do. Obviously, this would be for an isolated supercell case. That never happens when you're in the field, but it just hopes to give you an idea of kind of what we would expect a typical operating day to look like if it were perfect. So in terms of some of the measurements, you can see Dow 6, 7, and 8 kind of set up in this dual Doppler coverage lobe with the CAL, the C-band providing much larger coverage overview of the near storm convective environment. Near the storm, we'll have drones, 2 of them specifically, one sampling post-swath and one in the inflow region of the storm. We have the PSU armored vehicle that will be basically trying to launch windsondes into the updraft, so kind of a high-risk area. One of the NIU vehicles that has been outfitted with a hail cage from Tim Marshall will be near the forward flank in an area of significant potential hailfall, trying to launch windsondes as well. And then we'll have these further out far field teams that are launching full tropospheric depth radiosondes in the near storm environment. And these will basically be a leapfrog. One sounding is released, another team tracks that balloon, and then they leapfrog with an hourly cadence to sampling the convective environment. So we hope to have a lot of environmental information, both near storm, updraft, but also kind of far storm in the uncontaminated, hopefully uncontaminated inflow. You can see our Dow positions there on a perfect day. We should be getting solid dual Doppler coverage, at least from the X-band radars. If we can position potentially with an optimal, if there's a great day where we have low-level 88D coverage, we could set up the cow in a dual Doppler robe with an 88D. There would be some considerations of VCP and scanning strategy there that we could work out with a particular office if necessary. But the cow will hopefully provide us with some unprecedented radar observations, given it will be a C-band. The hailsonde drifters. This is the Bureau of Meteorology team. This is the team that will hopefully get close to the updraft and allow these kind of pseudo-Lagrangian drifters to get into the updraft so we can track their trajectories and hopefully constrain some of the vertical velocity measurements that we're getting from the dual Doppler lobe coverage. Again, that would be kind of in an ideal environment. As the storm gets ready to cross a road network, that will generally be our optimal time for sampling. In this case, we kind of have an eastward storm motion and a beautiful example of a north-south road that never seems to exist when you really want it to. But we would be measuring these super sites. Those are the ones I showed you earlier with the baffle and the collection into a cooler. We will have up to 4 of those, although Julian's trying to hopefully get as many as 6 of those super sites ready to go for ICECHIP. We will have hail pads distributed along that swath every 100 meters, and that will take about 20 or so minutes to lay all those down across an expected swath, depending on how wide, so to speak, the hail swath is potentially going to be as it crosses one of these opportunistic highways. We have the mobile impact astrometers, 24 of those from IBHS. These basically measure total impact kinetic energy and can tell us what type of hydrometeors and the size of those hydrometeors with very high precision. So IBHS will be deploying those along the potential hail swath as well. And then I also mentioned the 16-potted mesonets. These are more of your traditional stick net type of observations that will capture temperature, dew point, wind speed, and so on. That will give us a little bit more idea of the depth of the cold pool, inflow as the storm really gets close to the road. What are the various, potential temperature, equivalent potential temperature, perturbations in those variables as the storm passes over our network of observations. We also do have some optical Parseval distrometers, which operate in a little bit different way than the impacts do. The impact distrometers obviously rely on impact and kinetic energy. The optical distrometers actually use laser to understand exactly as the hailstone is falling through the optical portion of the sensor to characterize hail fall and hail size. And so we don't really want to put those in the greatest part of the hail swath because those are pretty pricey instruments. But we may deploy these on the fringes where we would potentially be expecting smaller hail. But you know how that goes. Put those out, and then of course they'll be destroyed on the first day of the campaign or something like that. So, and then our drones, the UAS from the Raven from Colorado to sample the hail swath in the post-storm environment as the storm rolls over the road. Hopefully that Raven team can get up very quickly and fly some cross sections of the swath so we can have some high resolution aerial imagery. Again, that drone will probably be flying between 80 and 100 meters AGL, so you can get some really high quality photographic data from that elevation with drones. And then a couple other just kind of your standard quadcopter types for augmenting pictures in specific areas or looking at damage to specific homes or whatever it might be. In the post-op, we actually do have one team. There's a Central Michigan team that will be launching windsondes in the post-storm environment. They are very interested in sampling the cold pool perturbation, not only temperature, but also depth of the cold pool as the convection, in this case, moves off to the east. They'll be doing that with windsondes and probably cutting those windsondes at maybe 2,500 meters AGL. So they're really interested in near-surface cold pool types of measurements for their specific science objective. Okay, where we're going to be operating, this is just a random kind of, it's not Microsoft Paint, but it's pretty close. I threw this together of, mostly here in the central and southern region, wherever there's hail. We're starting in Denver. We'll specifically be doing all of our training in Boulder from May 13th to 15th. Our first field operations day will be May 16th. We'll be departing from Boulder and we'll head wherever the greatest convective threat is. We'll obviously stay out of eastern Oklahoma. This is primarily chase country. There's certain areas in here that logistically are really challenging if you're trying to do radar. The Pine Ridge, right? The Sand Hills, the Black Hills, and so on. But this is primarily where we will be operating. The eastward extent, I think, is questionable. I mean, I could see us operating in days of Illinois and potentially Indiana if the pattern was so bleak that we had to operate there. But I think for the most part, given the amount of time that we're going to be out in the field, again, over 40 days, this will primarily be our operating region. And within that, we've sort of justified some, focus areas, and these are primarily based on mesh detections, climatology essentially, but also the types of environmental regimes that we would expect, where the early part of the campaign is really focused on kind of your traditional supercell type of hail events. And then we shift towards more upslope types of regimes with easterly surface flow and, weak to maybe marginal deep layer shear on the high plains. That still is pretty classic, supercell type of regimes to produce significant hail swaths. And those are typically, much different convective environments than the ones that you would, often sample for giant or gargantuan hail when you're looking for supercell type of, your traditional kind of dry line supercell environments that we'll be looking for early on in the campaign. So as we get deeper into June and we probably shift from the southern central plains to the northern and high plains, we'll be trading off these convective environments, and our not only our convective modes but our regimes that we'll be sampling will hopefully be quite a bit different. And I'm going to close just briefly talking about our themes, and then I want to give an opportunity for questions as well. Science themes are really embryo development. This is being led by NCAR, so wet growth, dry growth, fall behavior, fall speed. Do hailstones tumble? How much do they tumble? What axis do they tumble? Shedding, melting, all these different things that that will hopefully confine some of our hail microphysics schemes in hailcasts and in WRF that will obviously make their way to operational meteorology. These are the in-storm updraft relationships. There's a lot of questions right now about updraft width, updraft volume, updraft speed, how much shear is there in the hail growth region. So hopefully sampling some of those convective environments both via radar and radiosonde will be very helpful there. The environmental themes, so this is really capturing near storm environmental profiles, both windsonde and full depth radiosonde. You can see here some of our questions. We have a lot of modeling after the fact that will be dedicated to the campaign. So data denial experiments, types of observations, what can we improve hail forecasts if we had better observations, so to speak. I know I'm sort of saying that out of the side of my mouth right now as we lose several radiosonde observations across the country, but yeah, here we are. Theme 4 is ground deployment. So this is surface characteristics. Obviously, there are a lot of insurance companies, reinsurance companies, the agricultural community, aviation, that are very interested in surface hailstone characteristics. That will be led by IBHS and Central Michigan University to better characterize those. This will be not only in situ, but also remotely sensed via unmanned aerial vehicles. And then the significant amount of remotely sensed observations will come from radar, and that's being led by Matt Kumjian at Penn State, and Cam Homeyer at OU will be, I think, leading those observations and directing the dowels to the specific locations for better dual Doppler coverage and scanning of the hail growth and microphysics regions. So I want to kind of end there with just a slide of I want to really thank all of you, especially if there's any MICs or SUs in the room that wrote letters of support and letters of collaboration for this project. We plan to have live field communication via Slack and WhatsApp. Some of you already have those Slack invitations. If you're really interested in seeing what's going on, even if you just want to lurk into the Slack chat, we can get you an account set up on Slack, an invitation set up on Slack. When we're in the field, we'll primarily be communicating via WhatsApp, just because of the fast nature and ease of nature of communicating across a significant number of teams. And then, of course, quick decision making. So WhatsApp seems to be the easiest way there. I do have a question maybe posed for some of you of how to handle the LSRs. We don't want to really dismantle and blow up the hail climatology, although that's probably what's going to happen across the central region this year due to this project. So handling LSRs to individual offices, we obviously don't want to bombard you every 10 minutes with a new report. So we're toying around with a live Google map that will basically show our reports in real time as we enter them into our databases. We will have an LDM feed set up for all of our radiosonde data to the Storm Prediction Center. And if there's any local WFOs that really want to have access to the LDM feed, please reach out to me via email and we can get that set up. But right now we are just planning on sending that data to the SPC so they can use it for MCD and watch operations. And then I think there's other opportunities of VCP strategies if we're operating in your CWA. We've done a lot of outreach with Kokoros and getting people hail pads. If there's any record events that happen in your CWA, obviously we want to help you with those. If we're down for a couple of days and we happen to be in your area, an office field day would be fantastic. Invite the public or our team, and we could do a weather balloon launch or something like that. I realize you all are very short-staffed right now, and there's a lot of other moving parts and issues, and so I want to be very respectful of your time. But I think there's opportunities for community outreach and engagement with ICECHIP as well. And then, of course, any other science collaborations, if you're very interested or passionate about a specific topic that you're interested in here, we'd love to collaborate with you and work on bring you on as a science PI for a specific science objective that you might be interested in. So I'm at the top of the hour here. I'll pass it back over to Jenny. I don't know if we have time for any questions at all, but you know, be creative, be anything that you think that we're not thinking of that we should be. I'm all ears.
Great. Thanks so much, Victor. And I do know that a lot of our Central Region SUs are involved with this project, especially in the portion of the domain that was shown today. So if you do have some feedback, you could pass that to your SU and they would probably be able to communicate that in the ICECHIP collaboration room or in other ways. I think the biggest question is about the sharing of the data with the field. And while I know you guys don't have that fully finalized, I think there are some things that we could definitely do. Maybe have Seth look into the LDM feed and see if we could get that to our offices as well for those upper air soundings. And then definitely, I love the Google Map idea for the hail reports. We know where we're looking for reports. And not fortunately, but I don't think we'd have the time to totally bombard the hail database with LSRs. So we'd just mainly be looking in the places where we really need observations and would be able to go look for those data. So I think that would be really helpful.
Yeah, if you're looking to verify a warning, or there's not a lot of population for whatever reason, I mean, that might be an opportunity to pull up our Google map in real time and just say, oh yeah, they're finding golf balls there, or whatever it might be. So we're open to sharing the data. Both there will be real-time looks in radar as well too. So we have I'll share it with Jenny later on so she can disseminate it out. But basically, there's a field campaign website where we'll have all of our data in real time, and we'll have the links to the Google map and radius on data that will be populating in a live fashion. So
really appreciate it. I think we're at the top of the hour, so we'll let Victor go. But if you do have questions for him or want more information about the project, feel free to reach out to me or your Sue, and we will get you connected.